we have, in the copper zinc cell, we have zinc is a stronger reducing agent than copper. So in the copper zinc cell, the zinc is oxidized. Your zinc will form the, now which one is it? The cathode or the anode?
Anode.
Zinc will be the anode. Okay? And copper is reduced. No, the copper ions are reduced. Am I right? Copper ions will be reduced. So the copper Cu will be the cathode. So zinc is oxidized, it is the oxidation half cell, and the copper ions are reduced, so copper and copper ions forms the reduction half cell. So Zn goes to Zn2 plus 2 electrons, and Cu2 plus will take those 2 electrons and form Cu. So electrons will flow through the wires from the zinc to the copper. So this zinc anode, its mass will decrease, and the cathode's mass will increase. What will happen to the concentration of the zinc ions in the oxidation half cell? It will increase. What happens to the concentration of the copper 2 plus ions in the reduction half cell? It will decrease. So we need to help this reaction not to reach equilibrium, we need to prevent a charge buildup in the half cells. So what happens? That is where we have the salt breach. Okay? So this salt breach will allow anions to flow to the zinc half cell, ions will diffuse to the copper half cell. The copper zinc cell is an example of a galvanic cell, or some people like calling it a voltaic cell. So it's a galvanic or voltaic cell, and it's an example where we have a spontaneous redox reactions. So because the redox reaction is spontaneous, there is chemical energy being converted into electric energy. So one of the first people who built a cell like this was Volta, and that's why this type of cell is called a voltaic cell. And I think that is also why potential difference has the unit of the volts. So the oxidation half reaction is the zinc going to zinc 2 plus, and the reduction half reaction is the copper going to copper 2, the copper 2 plus going to copper. So what is the net redox reaction? What do? We say Zn plus Cu 2 plus going to Zn 2 plus and Cu. That's the net equation for this reaction. And what is the spectator in this reaction? Because we started off with copper sulfate solution with a blue color, the sulfate solution, the sulfate ions in the solution would be the spectators. And the zinc solution is a colorless solution. Well, mine isn't completely colorless, but I didn't filter that residue out there. My next big question is, what will happen to this blue color of the copper sulfate solution? As this reaction takes place, what happens to the blue color? It will get lighter. So the blue color, because the copper 2 plus ion concentration is decreasing, the blue color will fade. The blue will fade. It will get lighter blue. Yes.
What happens to the NaCl?
What happens to the NaCl? It tries to keep the two, the NaCl, the NAs will go to the copper, the Na pluses will go to the copper side, because there we are removing the copper 2 plus ions. So for every one copper 2 plus that is removed, there will be two sodium ions diffusing that way. And the chloride ions, because we're adding more zinc 2+ ions there, the chloride will migrate to the zinc half cell, trying to keep the charge balanced in the electrolytes. Okay, my next big question is, why would this thing go flat? Why would the battery go flat? Because this is technically a battery. Why or when? When will it stop giving you electricity?
When the CO2 plus finishes.
Yes, when there will be no more Cu2+. If the concentration of the Cu2+ drops to 0 moles per cubic decimeter, this thing will stop working. And on the other side, when will it stop working on the other side? Is another possibility why it will stop working. The zinc electrode will, it will what? Explode. No, it will be completely corroded. So if there's no more zinc electrode left in the cell, if it's eaten away, if everything went into solution, the cell can't function either. So for the sake of measurements, because a voltaic cell gives us a voltage, it gives us an EMF. So for the sake of that, we have standard conditions. Okay. So concentration of electrolytes must be 1 mole per cubic decimeter. And you'll see just now why I'm talking about the standard conditions for voltaic cells. The second thing, please check in your textbook, because what's the standard temperature?
25 degrees. That's good.
25 degrees Celsius. Okay? Because it's important to have a standard temperature for the sake of measurements, because temperature affects the speed, the rate of a reaction. And the faster the reaction takes place, the more the energy output will be. And concentration would affect the rate of the reaction as well. So when you start off with a voltaic cell and you want to measure things and compare different voltaic cells' output, you need to start off with the same concentration. So standard concentration is 1 mole per cubic decimeter. And the third one is for the sake of where we have gases. For the sake of gases, the gas pressure must be, you could say 1 atmosphere or 101,3 kilopascals. Now, in my experiment, I did not have standard conditions. I didn't worry about the concentration of the electrolytes there. And today is obviously much colder than 25 degrees Celsius, so that reaction is taking place slower. And there are no gases present, so we don't need to worry about atmospheric pressure. Okay. We'll talk about this thing and its effect a little bit later. I want to talk about cell notation next. Now, cell notation is a quick and short way to represent a voltaic cell. Instead of having to draw out the zinc electrode and to show the galvanometer and to draw the copper electrode and to draw out this whole situation here, instead of having to draw it out like this, there is a quick way to represent this. And the quick way is called the cell notation. Now, with the cell notation, the oxidation half cell is always written on the left-hand side. And it's easy to remember because O comes before R in the alphabet. So, reduction half cell. What happens in the reduction half cell is lost. The second rule is your electrode is first. And your electrode is lost. What is this electrode called again? The anode. So your anode will be first, and what's that electrode called again? The cathode will be lost. Okay? So what is the anode in the cell? It is zinc. Now zinc is a solid. And it's touching what? The zinc sulfate, but the sulfate is not part of the reaction, so I'll leave it out. It is touching the zinc 2 plus ions in the sulfate solution. Between the solid and the liquid or the solution, you put a slash. Okay? Between the oxidation half cell and the reduction half cell, you put a double slash. You could say that's representing the salt bridge. What's the cathode? Cu. Copper is the cathode. Okay? With copper being the cathode, it's a solid. Okay? What is copper touching? Copper 2 plus, which is in solution. And because it's a solution touching a solid, there's a slash between them. This is a lot of brand new information here. We are going to calculate The copper zinc cells.
I apologize for the interruption. If there are any learners who would be interested in going to the SEA workshop on the evening of the 22nd, worship on the 25th of July, please can you come see Mrs. van Sherman after school?
So what is not in the video is now the explanation where I spoke about the standard hydrogen half cell.
Please note that.
So the standard electrode potential, it gets something like that for zinc to zinc 2 plus. For the zinc half cell is what? You said minus, read it from the table, you see?
Minus 0.34.
No, that was the copper one. 0.76 volts. So this is when you connect a zinc half cell to a hydrogen half cell under standard conditions. What's the standard electrode potential for the copper half cell? It is 0.34 volts. Now the cell potential would be the cathode's potential minus the anode's potential. What is that? Cathode was copper, am I right? 0.34. Anode was zinc, minus 0.76. What would that give us? So it's 0.34 plus
1.1.
will give us 0.1. 1.1 volts. Sorry for pushing this, but I wanted to bring it all together so that it might make sense in future. We'll go through it again, but with another example.